Hey everybody, this is the first lecture from chapter 25. So in the fourth week, we're going to be doing chapters 25 and 26 together, and not all of the sections, but kind of bits and pieces from that. Chapter 25 has to do with capacitance. So I'm going to try to define what that is and calculate or show how to calculate the capacitance from a couple of different types of capacitors. The first capacitor we've seen already is the parallel plate capacitor that we actually already kind of calculated or looked at the electric field between a little bit. And we saw that when you have a parallel plate capacitor like this, right, positive Q charge on one side, negative charge on the other, you get a constant or uniform electric field in the center of the plates. So we're going to define something called capacitance for this type of capacitor, which is what it's called. And capacitance we're going to denote by the letter C. Now, what I kind of mean by a capacitor comes from the word capacity, which is really referring to the capacity of this device or this configuration of plates to store charge or hold charge. Right now, you might guess, right, that if I increase the voltage, it means I'm kind of moving more charge over from one plate to the other. I'm going to get more charge on the plates. So let's define capacitance. If you do some experimentation, you find that the amount of charge on the plates Q is proportional to that voltage, right? Bigger voltage, bigger charge. The proportionality constant, which depends on the geometry of the plates, is C, and that's our capacitance. So if you solve for C, you find capacitance is defined to be the charge on the plates, Q, right, either positive or negative, it's the absolute value of the charge, divided by the voltage between the plates. There's a special unit for this. It's a coulomb per volt, charge over voltage, but we call this a farad. So 1 farad equals 1 coulomb per volt, and we denote it by the letter F. Turns out the farad is a really large unit, and so oftentimes you will have units for capacitors of picofarads. In fact, you can go and buy, if you're doing circuits, you can buy these picofarad capacitors. They look like little cylinders, actually, a lot of the time, with wires coming out the end. I think there's a picture in the book of that. So the parallel plate capacitor isn't the only geometry, right? You could take that parallel plate capacitor, change the shape of it, and you'll still have a capacitor. In fact, you could take two pieces of metal, maybe two wrenches. If you got positive charge on one and negative charge on the other, you've got a capacitor. There's a certain amount of electric field between them, a certain amount of charge stored on those pieces of metal. But we're going to look at the parallel plate capacitor for right now and try to calculate or get a formula for the capacitance. Again, right, for the parallel plate capacitor, the electric field is constant, and it could be shown, and we didn't explicitly do this, it's actually done, you could do it by doing the integral like we did for a continuous line charge. I choose a point here between and add up the electric fields from all the charges on the plates. There's something called Gauss's law, which we kind of skip past, but either way, you can calculate the electric field. It turns out that it's related to the surface charge density, right? So the sigma is the charge on the plates divided by the area of the plates. So surface charge density divided by this permittivity constant, epsilon 0. Remember, I often like to use K. Sometimes I'll switch back and forth. The book likes to use K equals 1 over 4 pi epsilon 0, right? But it's just another way of writing that Coulomb constant. So you could write the electric field as sigma over 4 pi k if you wanted. But we're going to use this sigma over epsilon 0. And again, sigma is the surface charge density. So let's try to get the capacitance. First, we need the voltage in terms of the electric field. And we remember, right, voltage is electric field times distance if you have a uniform field. The negative sign here just tells me, well, it's negative if I'm going down from positive to negative, or tells me the sign, or depends on which way I'm going, but it's really telling me that the voltage drops if I go along the electric field. Now, I'm going to drop that negative sign because what we're really concerned about is C. It's just a number. It doesn't really have a positive or negative value. So dropping this, plugging in voltage into Q equals CV, right, we get this. Now I'm going to plug in my electric field is sigma over epsilon 0, so I just have E is sigma over epsilon 0 times D, and I solve for C. I find that the capacitance is epsilon 0 Q over sigma D, but again, using sigma equals Q over A, right, I can plug that in. Charges will cancel here, and I end up getting the capacitor for a parallel plate, two parallel plates, is epsilon 0 times the area of the plates over the distance of between the plates, right? So B is the distance between the plates here. So this is the formula you could use to calculate the capacitance of a parallel plate capacitor. One thing that kind of makes sense, right? The capacitance is proportional to the area. The bigger the plates, the more charge you can put on them per unit volt, right, per voltage. If the distance between the plates is bigger, well, the capacitance goes down, and that means you have to get a bigger voltage to put the same amount of charge. So it kind of makes sense, right? And again, it illustrates that what I mean by capacitance is the capacity of charge that you can easily store on those plates. Well, let's look at one other geometry real quick. Although in the book they do others like a spherical capacitor, we're going to look at a cylindrical capacitor here real quick. And this would be like a coaxial cable. So what you have is a cable, right? It's a cylinder, so I've only drawn a cross section of it. It's kind of like the wire is going into the page here. And I have a positive inner core, positive charge on my inner core here, and a negative charge on my outer shell, cylindrical shell. Now the length of the cable could be really long, and so what happens is when you do get the electric field, you get an L here. This L is the length of cable, or you could say this is the electric field per length of cable. But it turns out to be the charge, Q, either positive or negative, over 2 pi epsilon 0 L R. Right, so it depends on 1 over R. Now R, I mean in between, right? In between. This electric field is only for in between the coaxial cable pieces here. But again, right, if I want to get my capacitance, I first need to calculate my voltage from my electric field. Now, instead of just E times the distance, well, the electric field depends on the distance, R here. So I've got to do an integral. Plug in my electric field to that integral, right? Well, pull out all the constants, Q over 2 pi epsilon 0 L. I have integral of 1 over R, and I'm going from A to B. So what I mean is A is the inner radius of the inner core there, and B is the radius to the outer shell. Right? So I'm going from A to B, from the edge of the core here to the outer shell. Well, the integral of 1 over R dr is just the natural logarithm, so I end up getting this for the voltage. But again, capacitance is charge divided by this voltage. I'll kind of flip everything up over here, invert. When I divide by voltage, Q's cancel, and I get this expression for the capacitance of a cylindrical coaxial cable. Now it depends on the length, right? So the more length you have, well, the bigger the capacitance of that piece. So sometimes people might divide the L over here and say, oh, it's the capacitance per unit length of a coaxial cable. But either way, I think you can use this formula maybe in one of the problems from this chapter. Last thing, how do you use capacitors? Well, several ways, but usually the way that we use them is in an electrical circuit. And by a circuit, I mean I'm going to connect wires to my capacitor. Now I can charge up the capacitor. How do I put charge on it? Well, I connect it to a battery. So I'm going to denote a battery by the long and short line here. Long line is a positive terminal, right? Negative is, the short line is a negative terminal. So it could be like a 9-volt battery or something like that. And I'm going to connect wires and put it to my parallel plates. Now, even if it was a cylindrical capacitor, I would use this symbol for it, just 2 parallel plates. So it doesn't always have to be a parallel plate capacitor. It can be whatever capacitor I connect with those wires. Now, how do I charge up the capacitor? Well, I might have a switch, and when I shut it, I connect the circuit and charge starts to flow through the wires. And I get what's called a current. Now, as time goes on, more and more positive charge is going to flow here, and more, I guess, negative charge is left behind, right? So positive charges would kind of flow this way, come off of this plate and move to this plate, and I end up getting charge on my capacitor. Now, eventually, the voltage across the capacitor is going to build up and be opposite to the direction or the capacitor or the voltage on the battery. The current's going to stop. And at that point, no more current's flowing. I've kind of got charge stored on my capacitor here when the switch is closed for long enough. So another way to think of it is, well, whenever you have charge there, you've got energy. So a capacitor is kind of an energy storage device. I can release that energy in various ways by opening this, opening the switch, or I guess once I had it charged up, I could take the battery out, connect it to something else, and let that charge flow through that other device. I could discharge the capacitor. We haven't really defined current completely yet, although there was a problem about it. So we'll talk about charging and discharging capacitors more in the future. But I wanted to show you just kind of the beginning of a circuit here. In the next video, I'll talk about combining what happens if you have 2 or 3 capacitors in the same circuit. So that'll be the next topic, and we'll stop there for now.